Welcome to Act 1. How can a client use cloud computation without revealing private data? The roadmap moves from plain values to encrypted objects. TLS protects information in transit, but an ordinary server decrypts it before computing. Homomorphic encryption keeps the secret key with the client and allows only ciphertext to cross the trust boundary. The first experiment shows the outsourced compute dilemma. A private image begins with the data owner and moves toward useful cloud hardware. The transfer itself may be protected, yet the server eventually places a readable representation in memory. The scanning line and observing eye make the missing security state visible. The data is exposed while the computation is active. Encryption at rest protects a stored file, and encryption in transit protects network packets, but neither one automatically protects server memory. Homomorphic encryption targets this third state, called data in use. The goal is not to hide the existence of a request. The goal is to prevent the cloud from learning the input, intermediate features, or final numerical result while still carrying out the requested arithmetic. Now define the two trust domains precisely. The trusted client owns the private input and the secret key. The cloud is allowed to receive ciphertext and an evaluation program, but it is not given decryption authority. Watch the encrypted packet cross the dashed boundary, while the key remains on the client side. The crossed-out I means that the cloud can store and transform the ciphertext without reading its hidden values. This separation is stronger than simply calling one machine secure and another machine insecure. It assigns a specific capability to each object. The client may encrypt and decrypt. The server may evaluate the approved circuit. Only the client may reveal the answer. A clear trust boundary is therefore the starting point for both the cryptographic design and the deployment architecture. The tunnel on screen represents transport encryption such as TLS. The packet remains protected while it moves through the network. At the server endpoint, however, the tunnel ends. A conventional application decrypts the request, reconstructs the plaintext image, and places that image in memory so ordinary code can inspect and process it. This is why a secure channel is not the same thing as encrypted computation. TLS can prevent an outside observer from reading packets in transit, but it does not prevent the receiving service, a compromised process, or a memory inspection tool from seeing the decoded data. The visual change from ciphertext dots back into a readable grid marks that exact boundary. Protecting the route is necessary, but the computation itself requires a different mechanism. Run the same request again using homomorphic encryption. The client begins with a readable value, encrypts it into an opaque ciphertext, and sends only that ciphertext to the evaluator. The cloud applies the function without opening the hidden message. Notice that the object remains encrypted while it enters the evaluator, while the evaluator turns, and while the result travels back across the boundary. The returned object is enc of f of x, not the plaintext answer. Only after it reaches the client and meets the secret key does it become the visible score. This preserves privacy for the input, the intermediate encrypted state, and the output. The essential promise is simple. Useful computation occurs on the cloud, but decryption authority never leaves the trusted client. Stronger privacy has a measurable cost. 6 small plaintext values expand into a much larger ciphertext representation, so storage and communication increase. The 2 operation paths show a second limitation. Algebraic addition is directly supported, while a hidden branch such as if x is positive cannot be evaluated as ordinary control flow. The clock then shows the third cost. Operations on encrypted polynomials require far more work than operations on native numbers. These constraints interact. Larger parameters may provide more security, precision, or multiplication depth, but they also increase memory use and runtime. A practical FHE system therefore chooses the value layout, supported operations, parameter sizes, and circuit depth together. Homomorphic encryption is not free encryption around an unchanged program. It is a deliberate systems trade-off. The second chapter asks whether encrypted computation produces the correct numerical answer. We first follow X through encryption and evaluation, then compare exact integer schemes with approximate CKKS, and finally expose multiplication depth as a finite circuit resource. Correctness is the central invariant. The upper lane performs ordinary plaintext computation. It sends the value 2 through f of x equals x squared plus 1 and obtains 5. The lower lane starts from an encrypted version of the same value. The cloud applies evaluate f without learning the input and produces another locked object. When the client decrypts that result, the lower lane also reveals 5. In an exact scheme, the answers should agree exactly within the message space. In CKKS, the decrypted value should be numerically close because the scheme intentionally uses approximate arithmetic. The important comparison is between the two complete paths. Decrypt after encrypted evaluation should match ordinary evaluation within the permitted error. If those paths disagree, privacy alone is not enough. The computation is not useful. Encrypted circuits also have a resource budget. The stacked levels represent the active coefficient modulus chain. Each time the locked token passes through a multiplication, it moves downward and consumes part of the available depth. Additions are usually cheaper and do not spend a level in the same way. A leveled scheme chooses enough parameters for a known multiplication schedule, so the circuit must be planned before private data is evaluated. When the token approaches the bottom, bootstrapping offers a way to refresh it and return to a higher capacity state. That capability can support longer computations, but the large bootstrap gate and its warning label are intentional. Refresh is powerful and expensive. Good circuit design tries to control depth, scale, and precision before relying on a costly reset. Ordinary programs often branch after inspecting a value. The encrypted token cannot do that because the cloud does not know whether the hidden number is positive, larger than another number, or equal to a threshold. On screen, the token reaches the red if statement and stops at the wall. The replacement path is an arithmetic circuit whose structure is fixed in advance. Addition and multiplication gates do not need to inspect a secret condition. They apply algebraic transformations to every ciphertext that reaches them. This changes the programming model. Comparisons, maximum functions, secret-dependent indexing, and loops with hidden stopping conditions must be removed, approximated, or implemented through more specialized protocols. For CKKS workloads, program design moves away from control flow and toward polynomial-compatible arithmetic. Private inference does not require every object to be encrypted. The red feature map represents private client data and must remain ciphertext. The blue column represents public model weights that the server already owns. Both flow into the multiplication gate, where a ciphertext plaintext product applies the public weights to the hidden features. The output remains encrypted, and the crossed-out eye confirms that the server still cannot inspect the resulting activation. This arrangement is useful because multiplying by encoded plaintext constants is often cheaper than multiplying two ciphertexts. It also matches a common deployment model. The service provider may expose or protect its model under a separate policy, while the user requires confidentiality for inputs, intermediate activations, and outputs. The cryptographic boundary follows data ownership, not a rule that everything must look identical. The message type determines the scheme. Exact integers such as 7, 12, and 4 move into the BFV or BGV region, where arithmetic is performed over modular integer messages. Decimal values such as 0.25, -1.4, and 3.12 move into CKKS. CKKS accepts controlled approximation so that real or complex numerical workloads can be represented efficiently. The lower grid then shows its major performance feature. Many values can occupy SAMD slots inside one encoded polynomial and one ciphertext. A single homomorphic instruction can act across those slots in parallel. Computer vision relies heavily on real-value tensors and repeated numerical operations, so approximate packed arithmetic is usually the better fit for this course. The approximation is managed, measured, and kept within an application tolerance. The final chapter opens the ciphertext. A real vector becomes a ring polynomial. Encryption adds error. The result is a noisy polynomial tuple with finite resources. Why do polynomials appear? The four numerical values on the left begin as an ordinary vector. Each value moves to a coefficient position on the polynomial axis, where the stems make the new representation visible. The quotient ring circle then gathers that coefficient structure into the bounded algebraic workspace used by the scheme. Microsoft STL stores plaintext and ciphertext components as polynomials whose coefficients are reduced modulo an integer q. Addition combines coefficients efficiently, and multiplication uses fast polynomial arithmetic. The ring is not decoration around a hidden scalar. It is the actual language in which encoding, encryption, and homomorphic evaluation are expressed. This representation gives the library a finite machine object while preserving the algebra needed for valid encrypted operations. The next experiment explains how the quotient prevents polynomial degree from growing without bound. The circular path represents the quotient relation. We work in z sub q of x modulo x to the n plus 1, so x to the n is identified with -1. The token begins as the high-degree term x to the n plus 2. As it travels around the circle and crosses the x to the n boundary, its sign changes. It then lands at the x squared position and exits as -x squared. This is negacyclic wraparound. Powers do not continue growing forever and wrapping across degree, and introduces a minus sign. Only a few labeled positions are needed to see the rule. The quotient keeps every result below degree n, which makes repeated polynomial addition and multiplication remain inside one fixed dimensional ring. The RLWE picture combines three ingredients. The green row is a secret polynomial with small coefficients. The blue row supplies randomized public information, and the gray dots represent a small error term. All three enter the mixer, which produces two apparently noisy ciphertext polynomials. The error is not an accidental defect added after encryption. It is essential to the ring learning with error security assumption because it hides the exact algebraic relationship involving the secret. Without the secret key, recovering that relationship from many noisy samples is believed to be computationally hard for appropriate parameters. At the same time, the error cannot be arbitrary. It must remain small enough that legitimate decryption and decoding still recover the intended approximate message. Security and correctness therefore depend on the same carefully controlled noisy structure. There is no single counter that fully describes CKKS capacity. The three bars track related resources, coefficient modulus, remaining levels, and meaningful numerical precision. The locked token begins with a small error halo. After each multiplication, the active modulus and level capacity shrink while approximation effects accumulate. The halo expands and moves closer to the red failure threshold. Fresh encryption needs randomized error for security, but evaluation, rescaling, and finite precision encoding also influence the final numerical result. Parameters must leave enough headroom for the complete circuit, not merely for one operation. Correct decoding requires compatible scales, compatible parameter levels, sufficient modulus, and enough precision for the application tolerance. It is therefore more accurate to plan a combined modulus, level, scale, and precision budget than to speak about one generic noise number. The final transformation connects this foundation to the next scene. A real valued vector first enters a set of logical CKKS slots. The encoder maps those slot values into a polynomial representation and records a scale that preserves useful fractional precision. Encryption then turns the encoded plaintext into a tuple of noisy ring polynomials. The evaluator receives that ciphertext and applies only operations supported by the planned arithmetic circuit. Throughout the path, the visible numerical meaning and the polynomial object are different layers of the same computation. The client reasons about vectors and approximate results, while the cryptographic library manipulates coefficients, moduli, levels, and keys. Scene 2 will open the encoder in detail and show how slot packing, scale, rotations, and rescaling make this representation practical for numerical workloads. In the previous scene, we followed a real vector into a noisy polynomial ciphertext. We now continue from that bridge and open the CKKS representation itself. The first fact is that CKKS preserves useful numerical meaning, not exact bit patterns. On the enlarged number line, the blue point is the original value of pi, and the yellow point is the decoded result. They are extremely close, but they are not identical. The red arrow measures the small difference. What matters is whether the decoded point remains inside the green tolerance chosen by the application. For image features and neural network scores, numerical closeness is often the correct notion of correctness. To carry decimal information into ring arithmetic, the encoder first multiplies the value by a large scale. Watch 3.1415925 move into the wheel marked 2 to the power of 40. The scale shifts meaningful fractional information into a large integer-like magnitude. The growing precision marks represent the detail being preserved before rounding. The token then passes through the round operation and becomes polynomial-compatible data. The scale does not make the representation exact, and it is not merely a display unit. It is metadata that explains how the stored magnitude should later be interpreted. Choosing it too small loses precision early. Choosing it too large consumes modulus capacity too quickly. Decoding performs the reverse numerical interpretation. The stems on the left represent polynomial coefficients produced by the encoder. They are not a row of readable decimal values, yet together they carry the packed message. As the coefficients move through the divide by scale stage, the decoder reconstructs a slot value near 3.14159. The blue reference above it shows the original input. The short red distance between them is the residual approximation error. This visual is deliberately asymmetric. Encoding and decoding are not simple text formatting. They map between numerical slots and a ring element, while the tracked scale connects the two domains. A successful round trip preserves the useful digits required by the application. Approximation error does not enter at only one point. Follow the white token through the complete path. Encoding rounds a scaled value into ring data. Encryption adds randomized noise required by security. Homomorphic evaluation changes both numerical values and ciphertext state. Rescaling divides by a modulus prime and introduces another controlled rounding. Each colored contribution extends the same error bar rather than replacing the previous contribution. Good CKKS design therefore budgets error across the whole circuit. No single stage needs to be perfectly exact, but the accumulated effect must remain small enough that decryption and decoding still recover a meaningful numerical answer. The final test compares the encrypted computation with a plaintext baseline. The blue point marks the ordinary result and the red point marks the decrypted CKKS result. First, define the green tolerance band from the needs of the application. Then measure the absolute distance between the 2 points. Here the encrypted result remains inside the accepted region, so the test reports pass. A relative error check may also be important when output magnitudes vary widely. The key lesson is that tolerance is not an excuse for arbitrary error. It is an explicit numerical contract. The circuit, scale, modulus chain, and validation procedure must all be chosen, so the observed error satisfies that contract. now move from one approximate value to an entire packed vector. The upper row shows 6 independent input values. During encoding, each value moves straight into the slot directly below it, so the correspondence between input position and encoded position remains visible. The CKKS encode label marks this numerical transform. The slots together form one polynomial representation. They are not 6 separately encrypted scalars. In the final step, the complete slot row moves into one red ciphertext container. One ciphertext can therefore carry the whole vector. This packing is central to practical CKKS because one homomorphic instruction can be shared across every occupied slot. Slot layout must be planned as part of the algorithm before encryption begins. The number of available complex slots is tied to the polynomial modulus degree n. As the selector moves from 4096 to 8192 and then 16384, the visible grid expands and the counter changes from 2048 to 4096 and then 8192 slots. In CKKS, the standard packing capacity is n divided by 2 complex values. Larger n therefore creates more parallel capacity and can support a larger coefficient modulus budget. But the expansion is not free. Ring operations become more expensive, ciphertexts use more memory, and key material grows. The middle setting, n equal to 8192, gives 4096 complex slots in the educational configuration used later in this scene. Packed arithmetic behaves like single instruction, multiple data. The blue row and the yellow row each contain 4 slot values. Both rows enter one addition gate. The gate is invoked once, yet the 4 output positions appear together as 1 plus 10, 2 plus 20, 3 plus 30, and 4 plus 40. Multiplication follows the same slot-wise pattern. No slot automatically reads a neighboring slot, and the cloud still sees only encrypted objects. This parallel behavior is why a careful packing layout can make private inference practical. One ciphertext operation can update many image features, channels, or examples at the same time instead of paying the full cryptographic cost for every scalar. Public plaintext masks let us shape packed encrypted data cheaply. The red row contains encrypted values, while the green row broadcasts the pattern 1, 0, 1, 0, 1, 0. Multiplication by this mask leaves selected positions unchanged and suppresses the alternating positions. Watch the 0 selected cells fade before the yellow result appears. The server learns the public mask, but it does not learn the private values stored in the ciphertext. Similar masks can isolate channels, select lanes, or apply public weights. They are useful, but they do not move information between slots. They only transform each current position according to the plaintext value aligned with that position. To move information between positions, CKKS uses rotations. In the first phase, the vector 1, 2, 3 for shifts right by 1 position and becomes 4, 1, 2, 3. The Galois key shown beneath the arrow enables the automorphism and key switching step. It does not reveal the slot values. The first diagram then clears before the reduction begins. After one rotate and add stage, the partial sums are 5, 3, 5, 7. Rotating that partial vector by 2 positions gives 5, 7, 5, 3. Adding the 2 rows slot by slot produces 10 in every slot. This staged pattern builds packed sums, dot products, and convolution-like data movement without exposing the encrypted vector. Packing capacity is only one effect of the polynomial modulus degree. As the selector moves to larger n, the slot grid expands and the green capacity meter grows. At the same time, the red memory end time meter also grows. A larger ring dimension can support more slots and, under appropriate security limits, a larger total coefficient modulus. That may permit deeper computation or more precision. However, every polynomial operation, ciphertext, and evaluation key becomes more expensive. Parameter selection is therefore a balance among security, packing, precision, depth, memory, and latency. We do not choose the largest available end automatically. We choose the smallest secure dimension that can support the planned circuit and numerical target. Microsoft SEAL represents the coefficient modulus as a product of several primes. The four colored blocks Q3 through Q0 are the active residue number system components at the top of the chain. The rows below show successive data levels with fewer active primes. As the token descends, each row receives a different parameter identity because its modulus set is different. Ciphertexts can be added only when their important metadata is compatible, including level and scale. SEAL context validates the encryption parameters and builds this chain before computation begins. The visual reduction in active blocks is real resource consumption. Once a prime has been removed from a ciphertext level, ordinary evaluation does not simply restore it. Multiplication changes more than the encrypted numerical value. Both input ciphertexts here carry scale 2 to the power of 40. When they enter the multiplication gate, the product scale is approximately 2 to the power of 80. The red output and the rising gauge make that metadata growth visible. If we continued multiplying without managing scale and modulus, the represented magnitude would approach the available coefficient modulus ceiling and later operations would become incompatible or inaccurate. This is why CKKS code must inspect scale and chain position rather than treating ciphertexts as opaque numbers. Multiplication increases algebraic degree before relinearization and increases scale before rescaling. Both state changes must be handled deliberately. Rescaling brings the scale back to a manageable range by dividing by the final active modulus prime. Watch the last prime detach and fall away from the chain. At the same moment, the scale meter contracts from about 2 to the power of 80 toward 2 to the power of 40. The ciphertext then moves from level 3 to level 2, and the remaining primes shift together. This operation makes future additions and multiplications easier to align, but it permanently consumes one level and introduces controlled rounding. Rescaling is therefore not a free normalization step. The circuit must contain enough primes for every planned multiplication and rescale stage, with suitable bit sizes to preserve the required precision. The final diagram checks whether the parameter budget actually fits the circuit. On the left, the ciphertext starts at the top level and descends once after each multiplication. 3 multiplication stages therefore require 3 usable level transitions. On the right, the educational configuration uses polynomial modulus degree 8192, coefficient modulus bit sizes 60, 40, 40, and 60, and initial scale 2 to the power of 40. The comparison at the bottom makes the decision explicit. Depth needed is 3, levels available is 3, so the example reports a match. This does not make the configuration universal. A different model, security target, or precision requirement may need another degree, modulus chain, or scale. Parameters must be selected from the planned circuit, not copied blindly. Scene 2 showed how CKKS encodes and packs approximate values. We now continue by opening the ciphertext that carries those slots during computation. The red shell separates into two polynomial components, C0 of x and C1 of x. Inside each component, the color rows represent coefficients stored under several active residue number system primes. A real polynomial contains many more coefficients than the dots shown here, but the layered structure is the important idea. These are not two independent encrypted messages. Together they form one fresh ciphertext whose component count, or size, is commonly 2. Decryption explains why both components belong together. The visual expression combines C0 with C1 multiplied by the secret key polynomial S of x. Only the trusted client supplies that green key. The combination reconstructs the encoded message together with a small error term, which is expected in lattice encryption. The key then returns to the client instead of remaining beside the ciphertext. This picture is an intuition, not a complete security equation, but it shows the ownership boundary. A server may transform C0 and C1, while only the client can combine them with the secret key and decode the hidden slots. Polynomial coefficients are only part of the operational state. The central ciphertext now exposes 3 different kinds of metadata. 2 red dots show that its component size is 2. The yellow gauge records a scale near 2 to the power of 40, which tells CKKS how to interpret numerical magnitude. The colored modulus blocks identify the active parameter level. Microsoft Seal carries this information with the ciphertext because an evaluator cannot infer compatibility from the intended plaintext meaning. Size affects operation cost, scale affects approximate arithmetic, and the parameter's ID determines which modulus set is active. The next diagram demonstrates a metadata failure rather than merely naming it. Ciphertext A arrives at level 3 with scale S, while ciphertext B arrives at level 2 with scale 2S. Both arrows point toward an addition gate, but the gate flashes red because the states do not match. The lower operand is then adjusted to the compatible level and scale shown by the upper operand. Only after those labels agree does the gate turn green and emit a sum. In real code, level alignment and scale handling are separate decisions, but the visual makes the rule clear. Related numerical values are not automatically legal operands. A ciphertext can travel without transferring decryption authority. On the left, the trusted client keeps the secret key below the network path. The ciphertext is serialized into a row of byte packets and sent across the boundary. On the server side, a compatible SEAL context interprets the parameters and reconstructs a loaded ciphertext object. Notice that no secret key crosses the divider and no plaintext appears during loading. Serialization preserves the encrypted data and necessary representation, while key ownership remains separate. A mismatched context cannot safely interpret the object, so deployments must coordinate parameters as carefully as they coordinate the transmitted bytes. With compatible metadata, homomorphic addition follows the ciphertext structure directly. The top operand contains C0 and C1, and the lower operand contains D0 and D1. Matching components flow along separate paths. The first output becomes C0 plus D0, and the second becomes C1 plus D1. No third component is created, so a normal size 2 input pair produces a size 2 sum. After decryption and decoding, packed slots approximate element-wise addition. This operation is relatively inexpensive and usually does not consume another modulus chain level, although the operands still need compatible parameters and suitably aligned scales. Multiplication cost depends on which operand must remain private. On the left, encrypted X is multiplied by a public plaintext weight. The short green meter represents the cheaper path commonly used for known model parameters. On the right, both X and W are encrypted ciphertexts, so the red cost meter grows much farther. Protecting both operands requires polynomial products between ciphertext components and creates more state to maintain. This does not mean ciphertext plaintext multiplication is free. It can still increase scale and require later scaling. The comparison simply shows why public weights are valuable when the threat model allows them to remain unencrypted. Now watch two size 2 ciphertexts multiply. Components C0 and C1 meet D0 and D1 at the multiplication gate. The result expands into 3 components. The first contains C0 times D0. The middle combines the 2 cross terms, and the last contains C1 times D1. This third term is associated with a higher power of the secret key during decryption. At the same time, 2 inputs with scale s produce a result with scale near s squared. The diagram therefore reveals 2 independent consequences of multiplication. The component count grows from 2 to 3, and the numerical scale grows as well. Relinearization handles the extra component without decrypting the ciphertext. The 3-component result enters a key-switching block. Relin keys arrive through the green arrow and provide evaluation material related to higher powers of the secret key. The E2 component is absorbed by that transformation, and the output returns to 2 components, R0 and R1. The closed lock remains visible because the server has changed representation, not learned the message. Relinearization reduces future storage and computation, but it does not lower the CKKS scale, and it does not restore a consumed modulus level. Those are different maintenance problems. The 3 maintenance stages now appear in their normal order. Multiplication first changes the encrypted value, expands 2 components into 3, and raises the scale. Relinearization then uses evaluation keys to return the representation to 2 components. Rescaling finally shortens the active modulus chain and brings the scale back toward its planned range. Follow the dots, scale bar, and level blocks rather than treating the boxes as interchangeable cleanup commands. Each stage repairs a different consequence of encrypted multiplication. A correct evaluator schedule places these operations deliberately because changing their order can produce incompatible metadata or waste scarce modulus capacity. Coefficient modulus levels behave like a descending resource ladder. Ciphertext A begins on level 3, while ciphertext B is already on level 2. Sending both directly to the addition gate causes a compatibility warning. A modulus switch moves it downward by removing the final active prime, so it reaches the same parameter level as B. Their arrows can then enter the green gate and produce a sum. The direction matters. Ordinary evaluation can move a ciphertext down the chain, but it cannot recreate a prime that has already been removed. Circuit planning must therefore decide where operands meet before either path descends too far. Modulus switching and CKKS rescaling both remove an active prime, but the side-by-side animation shows why they are not identical. On the left, mod switch drops the final blue block while the displayed scale remains S. On the right, rescale drops the corresponding yellow block and changes a scale near S squared back toward S. Rescaling divides the encoded magnitude by the removed prime, so the decoded value remains approximately stable. In practice, library behavior and valid scale adjustment depend on the scheme and parameters. The durable mental model is to track two coordinates after every operation, the modulus chain level and the numerical scale. Rotations move information between packed positions. The source row contains 1, 2, 3, 4. A curved arrow requests a cyclic rotation to the right by one slot. Galois keys appear below and feed the key switching step required by the automorphism. The resulting row becomes 4, 1, 2, 3. The first value did not travel through plaintext memory, and the server did not inspect any slot. It applied an authorized encrypted permutation. Applications generate only the rotation keys they plan to use, because every additional key consumes memory. Slot layout and required shifts should therefore be decided before key generation. A packed product combines slot-wise multiplication with rotations. The blue feature vector 1, 2, 3, 4 is multiplied by the green weight vector 2, 1, 0, 3. One ciphertext operation produces the red products 2, 2, 0, 12. A rotate by 1 copy is added to form the first partial sums. A rotate by 2 copy is then added to that partial row. The final green row contains 16 in every displayed slot, matching the ordinary dot product. Real implementations may keep the result in one target slot instead, but the staged reduction demonstrates how cross-slot aggregation emerges from rotation and addition. The final blueprint turns these operations into a circuit plan. The encrypted path contains 3 multiplication nodes, and each is followed by a planned rescale marker. A purple rotation connects the data positions needed by the reduction. The counters below record multiplicative depth 3 usable levels, rotations by 1 and 2, and an initial scale near 2 to the power of 40. These are design decisions made before private input arrives. The evaluator does not improvise a missing level or rotation key at runtime. Scene 4 can now examine how public, secret, relinearization, and Galois keys provide exactly the capabilities this planned circuit requires. Scene 3 showed relinearization and rotations using special evaluation keys. We now continue by asking who creates each key and what capability it grants. Key generator samples hidden polynomial material and produces the secret key S of X. The key moves directly into a protected client vault. When an encrypted result arrives, the client combines that ciphertext with the secret key and recovers a plaintext object. The lock remains around the key because decryption authority is never sent with ordinary evaluation data. Losing this one capability compromises confidentiality, so secret key storage defines the trusted boundary of the application. The public key grants a different capability. The key owner can copy it to an approved data producer without exposing the secret key. Inside the producer region, a plaintext vector enters the encryption operation together with the shared public key. The first output is ciphertext A. Repeating randomized encryption on the same input produces ciphertext B with a different representation. Both decrypt to the same encoded value, but their bytes need not match. Public, therefore, means distributable for encryption, not meaningless. Architects still decide which producers receive the key and which contexts are allowed to use it. Relinearization keys support maintenance after ciphertext multiplication. The enlarged ciphertext begins with three components, E0, E1, and E2. It enters a key-switching block while real keys arrive through a separate green path. The extra component is absorbed, and the output returns to R0 and R1. The closed lock underneath shows that the result remains encrypted throughout the transformation. Real keys provide information related to higher secret key powers, so they are sensitive evaluation material, but they do not perform normal decryption. Their capability is narrow. Reduce representation size so later encrypted operations remain manageable. Galois keys authorize movement between packed slots. The source vector contains 1, 2, 3, 4. A key for rotation by 1 produces 4, 1, 2, 3. A separate key for rotation by 2 produces 3, 4, 1, 2. The two colored paths make the authorization explicit. Generating one rotation key does not automatically grant every possible shift. Microsoft Seal can package several requested automorphisms into Galois keys, but each capability increases key material. The circuit should list its required rotations before key generation so the deployment creates useful movement without provisioning unnecessary operations. Least privilege now becomes a concrete key policy. The secret key attempts to cross the client-server boundary and is blocked, then returns to the client. Public key, real keys, and only the required Galois rotations cross through separate approved paths. The bars below compare generating every possible rotation with generating only the 2 shifts used by the circuit. The shorter green bar represents less memory and a smaller capability surface. Evaluation keys still deserve protection and auditing, even though they cannot directly decrypt ordinary ciphertexts. A secure design sends the server exactly what its planned program needs and nothing more. The Microsoft Seal workflow starts by constructing encryption parameters. The left panel selects the CKKS scheme, polynomial modulus degree 8192, and a coefficient modulus chain with 60, 40, 40, and 60-bit primes. These choices enter SAL context as one configuration rather than unrelated settings. The context validates whether the scheme is supported, the security constraints are acceptable, and the modulus chain is structurally valid. Only after all checks pass should the application create dependent objects. Parameters define the cryptographic universe. Changing them later creates a different compatibility domain. A valid SAL context builds the linked modulus chain used during evaluation. The rows descend from level 3 to level 0, and each lower row contains fewer active primes. As the white token visits a row, the matching parameter's ID appears on the right. That identity is not a human-readable level number stored for decoration. It connects plaintexts and ciphertexts to exact context data. Objects at different parameters identifiers cannot simply be combined because their coefficient moduli differ. The context therefore supplies both precomputation and the compatibility map used by encryptor, evaluator, decryptor, and serialized objects. Key generator follows the capability plan derived from the circuit. The first branches create the secret key, public key, and relinearization keys. The purple branch creates Galois keys only for rotations by 1 and 2, matching the earlier reduction schedule. This ordering matters. The application should know its operations before requesting large evaluation key sets. The secret key remains the root decryption authority, while the other objects support encryption or selected evaluation tasks. Key generator does not decide the deployment policy automatically. Developers must serialize, distribute, protect, rotate, and eventually retire these objects according to their distinct capabilities. Encoding and encryption are separate transformations. On the client, a numerical vector enters CKKS encoder and becomes a plaintext ring representation at the plan scale. Encryptor then uses the appropriate key to randomize that plaintext into a ciphertext. Only the ciphertext crosses into the cloud region, where evaluator can add, multiply, or rotate it. The secret key remains below the client pipeline. Keeping these stages visually separate prevents a common misconception. Encoding changes numerical representation but provides no confidentiality, while encryption protects the encoded data. Correct applications must manage both numerical metadata and cryptographic ownership. Evaluator is the server-side workbench. An input ciphertext enters the purple region and passes through multiplication, rotation, and addition nodes. Real-in keys and Galois keys support the specific maintenance and movement operations shown below. The output is still a red encrypted result. Across the boundary, the client retains the secret key, and the dash separation states that this key never enters evaluator. The server may learn the circuit structure, operation sequence, ciphertext sizes, and runtime behavior, but it does not receive ordinary plaintext values. Evaluation is powerful computation over protected objects, not a hidden form of decryption. The complete deployment begins with the arithmetic circuit, not with a random parameter preset. The packed input enters 3 multiplication nodes before reaching the output. A purple arc records the rotations required by the reduction. The counters below summarize the design. Multiplicative depth 3, 2 rotation steps, and 4,096 available slots. Unsupported branches and comparisons must already have been rewritten into compatible arithmetic. These counts become requirements for scale, modulus levels, evaluation keys, memory, and latency. Designing the graph first prevents cryptographic setup from becoming trial and error after private data arrives. Circuit requirements now drive parameter selection. Depth 3, 4,096 slots and roughly 40 bits of working precision enter the configuration stage. The example selects polynomial modulus degree 8192, a 60, 40, 40, 60 coefficient modulus chain, and initial scale 2 to the power of 40. The completed configuration enters SAL context, which reports valid only when the settings satisfy its checks. This diagram illustrates the reasoning flow, not a universal recommendation. Production systems must use current security guidance, actual workload measurements, and the library's validation rules rather than copying educational numbers without analysis. After validation, the client provisions capabilities before processing data. Key generator creates the secret key, which follows the short green path and remains on the client. Copies of the public key, reeling keys, and only Galois rotations 1 and 2 travel across the boundary to the server. Separate arrows make the ownership policy visible. The server receives enough authority to accept encrypted inputs and execute the planned circuit, but not enough to perform normal decryption. Key files, parameter files, versioning, access control, backups, and rotation procedures all belong to this provisioning stage. Data can now follow the prepared route. The client starts with a packed numerical vector, encodes it, and encrypts the resulting plaintext. The red ciphertext crosses the boundary and passes through multiplication, rotation, and addition nodes on the server. At no point does the server display a decoded slot value. The final object remains an encrypted result and returns through the application protocol. Real programs must track scale, level, size, and parameter identity along this path, but those decisions were already scheduled during circuit design. Remote evaluation should execute a plan, not improvise around metadata failures. The trusted client completes the lifecycle. The encrypted result enters decryptor, then the recovered plaintext enters the decoder. On the number line, the blue point is the ordinary plaintext baseline and the red point is the FHE result. Both lie inside the green accepted tolerance, so the numerical check reports pass. The final row reminds us that correctness alone is not enough. Deployments also measure security, accuracy, latency, and memory. Act 1 therefore ends with one connected mental model. Design the computation, validate parameters, provision minimum capabilities, evaluate encrypted data, and verify the return numerical result.
In a standard convolutional neural network, The architecture typically involves convolution, batch normalization, and a ReLU activation. However, when we transition to fully homomorphic encryption to protect user data, we face a fundamental restriction. FHE only natively supports one-dimensional vector addition, multiplication, and rotation. Because the ReLU function relies on a maximum operation, it is not a valid polynomial and cannot be directly evaluated on encrypted data. To adapt these networks, we must replace the nonlinear ReLU with polynomial approximations. But this introduces a significant conflict between the multiplicative depth, meaning the number of multiplications, and the approximation precision. If we use a low-degree polynomial, it is computationally fast and requires less bootstrapping, but the approximation is poor and necessitates network retraining. Conversely, if we construct a high-degree approximation, such as a composed polynomial of degree 7 times 7 times 27, the fit against the ReLU function is highly accurate, eliminating the need to retrain the network. However, evaluating such high-degree polynomials consumes our multiplication budget rapidly, triggering expensive bootstrapping operations that severely degrade inference speed. Beyond the degree, the choice of polynomial basis is also crucial. While standard power basis is simple, employing orthogonal polynomials like Chebyshev or Hermite polynomials allows the network to capture and preserve more information during the approximation of activation functions. It is also important to correctly calculate the evaluation cost, defined by the multiplicative depth. For instance, computing x to the power of 4 does not require 3 sequential multiplications. We can first compute x squared, and then square that result, meaning x to the power of 4 only consumes a depth of 2. In modern implementations, we typically favor low-degree polynomials to ensure fast inference, which requires retraining the network. This brings a new challenge: numerical instability during training. During backpropagation, polynomial activations can easily cause exploding gradients. While we can clip gradients during backpropagation, forward propagation issues cannot be fixed with simple clipping because the maximum function is too expensive in FHE. The state-of-the-art solution is to introduce basis-wise normalization, normalizing each polynomial degree separately before aggregating them with trainable weights, effectively stabilizing the training process. To bypass the nonlinearity barrier of homomorphic encryption, we must turn to numerical analysis. Since the encrypted domain natively supports only addition and multiplication, we must replace the non-differentiable ReLU function with a smooth polynomial curve. A naive Taylor series expansion fails drastically as activation values grow away from the origin. Instead, we use minimax approximation to minimize the maximum error over a specific interval, allowing the network to retain nonlinearity purely through arithmetic. However, higher degree polynomials come at a severe cryptographic cost. Every multiplication consumes a level in our modulus chain, known as the multiplicative depth. But evaluating the cost is non-trivial. For example, computing x to the power of 4 does not require 3 sequential multiplications. By computing x squared and then squaring the result, the multiplicative depth is only 2. Thus, tracking the true depth is critical for efficiency. Furthermore, not all polynomials are born equal. Instead of the standard power basis, using orthogonal bases like Chebyshev or Hermite polynomials captures the data distribution more effectively. To balance accuracy and latency, the AutoFHE framework automates the search for optimal polynomial degrees. It dynamically assigns low-degree polynomials to layers that tolerate error, and high-degree approximations only where mathematically necessary. Eventually, deep evaluations consume the depth budget, and the ciphertext must be refreshed via bootstrapping. But CKKS packing introduces a hidden danger. During the heavy transformations of bootstrapping, numerical errors leak into the imaginary component. In deep networks, this imaginary leakage amplifies catastrophically. To prevent this, imaginary removing bootstrapping systematically projects the ciphertext back to the real subspace, cleansing the noise completely. As we transition neural networks into the encrypted domain, a naive approach might be to encrypt each individual pixel into its own separate ciphertext. While mathematically sound, this mapping is disastrously inefficient. The CKKS encryption scheme operates on massive polynomials, acting as a powerful vector processor. A single ciphertext can natively pack thousands of complex valued slots. If we place only one scalar pixel into this structure, we are utilizing a fraction of a percent of the available cryptographic bandwidth. The remaining slots are filled with zeros or cryptographic noise. Yet, despite being empty, they still incur the massive computational cost of homomorphic evaluation of the entire polynomial. This extreme underutilization directly triggers a far more fatal bottleneck, the bootstrapping traffic jam. Because our image data is distributed across thousands of nearly empty ciphertexts, evaluating a convolutional layer requires an astronomical number of sequential homomorphic multiplications. Each multiplication rapidly consumes the multiplicative depth of the ciphertexts. When this depth is exhausted, every single sparse ciphertext must individually undergo bootstrapping to refresh its noise budget. Bootstrapping is the most computationally expensive operation in FHE. Forcing the server to sequentially bootstrap thousands of mostly empty ciphertexts creates a massive processing queue. The inference latency skyrockets from seconds to days, grinding the throughput to an absolute halt. A paradigm shift in data packing is strictly required. To overcome the severe inefficiencies of naive encryption, researchers introduced a paradigm shift: multiplexed parallel convolutions. Instead of assigning a single pixel to a colossal ciphertext, we can deeply pack the data. By interleaving spatial pixels and multiple feature map channels into a single, unified vector, we can achieve nearly 100% slot utilization. The sparse, empty voids of the ciphertext are now dense with information, allowing the CKKS scheme to act as a massive SIMD processor, evaluating thousands of pixels simultaneously. This dense packing strategy unlocks a profound mathematical advantage during homomorphic convolution. In standard evaluation, sliding a kernel over an image requires a massive number of ciphertext rotations, which are computationally exorbitant. However, with multiplexed packing, the channels are systematically aligned. A single shared homomorphic rotation can shift the entire batch tensor at once, evaluating convolutions across multiple channels concurrently. This elegant alignment reduces the required number of rotations to a mere 38% compared to naive layouts, drastically slashing the inference latency. By combining continuous polynomial approximations, optimized degree trade-offs, imaginary removing bootstrapping, and multiplexed parallel convolutions, the impossible becomes possible. We can now construct deep, encrypted neural networks. Data flows through residual blocks, safely shielded by cryptographic noise. When the multiplicative depth runs low, our stable bootstrapping refreshes the ciphertext, projecting it back to the real subspace. This holistic architecture successfully evaluates ResNet 20 and even ResNet 110 over fully homomorphic encryption, achieving unprecedented speedups and maintaining a strict 128-bit security target.
Welcome to the third and final act of our comprehensive exploration into fully homomorphic encryption. Throughout the previous acts, we laid down the rigorous mathematical foundations of lattice-based cryptography, and we examined how to adapt complex deep learning algorithms, specifically convolutional neural networks, to operate within these strict mathematical boundaries. Now, it is time to bridge the gap between theoretical cryptography and real-world deployment. In this act, we will demonstrate practical, high-stakes applications of FHE. Our first system is CryptoFace, a state-of-the-art, end-to-end encrypted biometric facial recognition system. Biometrics represent the ultimate frontier of digital privacy. Unlike passwords or PIN codes, which can be easily rotated, reset, or changed if a database is compromised, your biometric identity is entirely immutable. You cannot change your face. Once your facial data is digitized and leaked, it is compromised forever. This absolute permanence makes traditional cloud-based biometric systems extremely dangerous targets for cyber attacks. To understand the absolute necessity of the CryptoFace architecture, we must first examine the critical vulnerability inherent in modern digital infrastructure. Consider the standard cloud computing model currently displayed on screen. On the left, we have the user's local device, capturing a high-resolution image of their face. On the right, we have a powerful, centralized cloud server equipped with advanced neural networks capable of verifying identities. In a traditional setup, the user transmits their plaintext face to the cloud. We typically rely on standard cryptographic protocols, such as Transport Layer Security, TLS, to protect this data while it is in transit. However, this creates a false sense of absolute security. The fundamental flaw lies in what the cybersecurity industry calls data in use. In order for the cloud server's neural network to process the image and extract facial features, the data must be completely decrypted into plaintext within the server's random access memory. This mandatory decryption creates a massive attack surface. If a malicious hacker exploits a zero-day vulnerability, or if an insider threat compromises the server infrastructure, your raw, unencrypted facial data is instantly exposed. Even if the cloud provider is not actively malicious, a model we define as the honest but curious adversary, they still have full technical access to your sensitive biometric profile. The tech industry has spent billions securing data at rest and data in transit, but data in use remains the Achilles heel of modern computing. This is the exact moment a catastrophic data leak occurs. CryptoFace was engineered to completely eradicate this vulnerability by introducing a fundamentally new approach to biometric authentication. Watch as we transition from the vulnerable traditional model to the fully homomorphic encryption paradigm. Instead of sending a plaintext image, the user's local device now mathematically locks the facial data using their public key before it ever touches the network interface. This produces a secure, high-entropy ciphertext block. This encrypted payload is then transmitted to the cloud. Here is where the mathematical magic happens. The cloud server receives the ciphertext and passes it directly into its deep learning algorithms. Because of the homomorphic properties of the encryption scheme, the server's neural network can perform convolutions, matrix multiplications, and feature extractions directly on the encrypted tensors. It literally computes blind. There is zero decryption happening on the server. No secret keys are ever shared. The computation is executed, the identity is verified, yet the cloud provider, the network administrators, and any potential hackers see nothing but unintelligible cryptographic noise. We successfully achieve the immense computational power of cloud AI, strictly bound by the absolute privacy of local processing. To successfully integrate fully homomorphic encryption with deep learning, we must immediately confront the most formidable barrier in modern cryptography, multiplicative depth. Look at the challenge currently presented on the screen. In standard computer vision tasks, achieving high accuracy in facial recognition typically requires extremely deep convolutional neural networks, stacking dozens of layers as seen in standard ResNet or VGG architectures. However, the CKKS homomorphic encryption scheme operates under the learning with errors mathematical assumption. This means every ciphertext inherently contains a foundational layer of cryptographic noise. While homomorphic addition scales this noise linearly and safely, homomorphic multiplication, which is strictly required for every convolutional filter and polynomial activation function, causes this noise to grow exponentially. Watch the diagram. If we force an encrypted image through a standard, deep CNN, the network performs thousands of sequential multiplications. As the ciphertext progresses through these deep layers, the noise accumulation becomes catastrophic. Long before the network reaches its final output layer, the designated noise budget is completely exhausted. The mathematical error overtakes the actual encoded biometric data, leading to what we define as CKKS data collapse. The resulting ciphertext is permanently corrupted, decrypting into entirely random, unintelligible garbage. Therefore, applying traditional deep learning architectures directly to encrypted data is mathematically impossible. As system architects, we cannot alter the fundamental laws of lattice cryptography to accommodate deep networks. Instead, we must fundamentally redesign the neural network architecture to accommodate the cryptography. Notice the transition on the screen to the CryptoFaceNet solution. Instead of feeding the entire high-resolution facial image into a single, massive neural network, the system employs a patch-based processing strategy. The input image is algorithmically divided into a grid of discrete, non-overlapping squares, represented here by the $4 × patch grid. Each of these localized patches contains specific facial textures, such as the curve of an eyebrow, the geometric edge of a jawline, or the microtexture of the iris. By breaking the global image down into these independent local components, we drastically reduce the complexity of the feature extraction task required for any single section of the encrypted tensor. With the facial data fragmented into patches, we can now leverage the computational supremacy of the CKKS scheme, the single instruction, multiple data, or SIMD property. Watch as the patches are distributed across the system. Instead of processing the entire face through a deep sequential pipeline, each encrypted patch is routed into a highly specialized, incredibly shallow neural network known as a patch CNN, or PCNN. Because these PCNNs are intentionally shallow, consisting of only the absolute minimum number of convolutional layers necessary to extract local features, they require an extremely low multiplicative depth. By executing these shallow networks in parallel across all patches simultaneously, we achieve two monumental victories. First, we completely prevent the catastrophic noise accumulation, ensuring the ciphertext remains fully decryptable. Second, we drastically reduce the computational latency on the cloud server. Having solved the neural network bottleneck, we can now map out the complete, end-to-end lifecycle of the CryptoFace system. On screen, we are establishing a strict zero-trust architectural layout. The vertical divider represents the network boundary, separating the trusted, local client environment on the left, from the untrusted server or cloud environment on the right. Furthermore, the horizontal divider separates the two primary chronological phases of biometric security. The top quadrants will handle the enrollment phase, where a user registers their identity for the very first time. The bottom quadrants will handle the verification phase, where a user attempts to authenticate themselves months or years later. Let us trace the exact cryptographic flow of data through these quadrants. Let us now direct our attention to the top half of our architectural layout, which represents the enrollment phase. In any biometric security framework, the lifecycle must begin by establishing a foundational ground truth, a reference profile for the user operating strictly within the secure confines of the trusted client environment, such as the user's personal smartphone or a highly secure registration terminal. The system initiates the capture process. As you can see, a high-resolution reference face is captured by the camera. Simultaneously, a plaintext identity ID, such as an employee number or a username, is generated to tag this session. In a traditional, legacy system, this highly sensitive, raw biometric photograph would simply be transmitted directly to the central server for processing. But in the zero-trust cryptoface architecture, this raw data is strictly prohibited from leaving the client device. Instead of transmitting the image, the client device invokes a local cryptographic module. Notice the encryption box appearing on the screen. The device generates an asymmetric cryptographic key pair based on the ring learning with errors assumption. It utilizes the public key to mathematically lock the raw image. During this encryption process, the pixel intensity values of the facial image are mapped into high-dimensional polynomial rings, and a carefully calibrated layer of mathematical noise is injected to completely obfuscate the underlying data. The output of this operation is the ciphertext you see now. The plaintext face has been completely destroyed and replaced by an impenetrable cryptographic vault. Because the client used a public key, the data is securely locked, but the corresponding secret key, the only mathematical tool capable of reversing this process, remains safely stored. The ciphertext now securely crosses the network boundary to the untrusted server. Now we witness the most groundbreaking capability of fully homomorphic encryption, homomorphic feature extraction. The untrusted cloud server receives the encrypted facial image. Watch as the ciphertext is fed directly into the server's patch convolutional neural network. Remember, the server does not hold the secret key, so it cannot see the face. However, by performing homomorphic additions and multiplications on the polynomial structures, the neural network essentially computes blindly. The convolutional filters slide across the encrypted data, successfully identifying edges, contours, and complex facial patterns without ever revealing the image itself. The output of this neural network is a highly compressed, encrypted reference vector, an embedding that captures the absolute biometric essence of the user. The server has successfully executed complex artificial intelligence on pure cryptographic noise. Finally, we reach the conclusion of the enrollment phase, blind storage. The cloud server takes the newly generated, highly compressed encrypted reference vector and stores it securely inside its centralized database. To ensure this encrypted biometric profile can be retrieved in the future, the server maps it to the plaintext identity ID that was provided by the client at the beginning of the session. The user is now fully enrolled in the system. The beauty of this architecture is absolute privacy. If a malicious hacker were to breach the server's database right now, or if a rogue database administrator attempted to view the records, they would not find any faces. They would only find random, unintelligible polynomial coefficients. The baseline security has been mathematically guaranteed. We now move to the bottom half of our architectural diagram, representing the verification phase. Imagine it is now months, or even years, after the initial enrollment. The user is attempting to access a highly secure facility or unlock a digital vault. Operating once again within the trusted client environment, the local camera captures a fresh, live biometric reading, known as the probe face. Simultaneously, the user provides a claimed ID, asserting who they are supposed to be. Just as in the enrollment phase, the Zero Trust Protocol mandates that this live biometric data cannot be exposed. The client device immediately invokes the cryptographic module. It applies the same public key to the live probe face, injecting fresh mathematical noise, and generating a brand new ciphertext. This securely locked probe face is now transmitted across the network to the untrusted cloud server. From the moment the camera snapped the picture, the data was secured. Upon receiving the data, the cloud server initiates two parallel operations. First, it reads the plaintext claimed ID. It uses this identifier to query its centralized database and retrieve the user's original, encrypted reference vector, the exact same ciphertext that was blindly stored during the enrollment phase months ago. Simultaneously, the server routes the newly arrived, encrypted probe face into the patch-based convolutional neural network. Once again, the network computes blindly. It performs homomorphic feature extraction on the live biometric data, eventually outputting a brand new, encrypted probe vector. The server now holds two distinct, highly compressed encrypted arrays, the reference vector from the past, and the probe vector from the present. The challenge now is to determine if these two vectors belong to the same human being, without ever decrypting them. To determine similarity, the server performs secure comparison. It homomorphically calculates the distance between two vectors, outputting an encrypted score. In traditional programming, verifying this score is trivial. The server would use a conditional if statement. If the score is less than security threshold, grant access. However, fully homomorphic encryption prohibits conditional branching. The server cannot evaluate an if statement because it cannot see numbers. It cannot know if score is smaller or larger than threshold. To bypass this, the server performs one final homomorphic operation. It subtracts the predefined security threshold from the encrypted score. The formula result equals score minus threshold is executed entirely in encrypted domain. The output is a highly secured, locked result box. The server has completed authentication logic, yet remains completely unaware of whether verification was successful or failed. Because the server is mathematically blind to the outcome, it must return this locked result box to the trusted client. As the ciphertext crosses back over the zero-trust boundary, the client device receives the payload. It applies the exclusive secret key, which has never left the local hardware, to the decryption module. The complex lattice noise is instantly stripped away. The client device evaluates the underlying plaintext result. Because the original homomorphic score was lower than the threshold, the plaintext result is a negative mathematical value. The local client recognizes this negative value as a definitive cryptographic match. Access is granted. The biometric authentication is complete. The user has successfully verified their identity utilizing the massive computational power of the cloud, while mathematically guaranteeing that neither their facial data, nor the outcome of the authentication, was ever exposed to the server or the network. Welcome to the architectural deep dive of HERS, the privacy-preserving health record system. In this specific scenario, we are addressing a fundamental security flaw in how modern telemedicine handles sensitive data. Consider the current landscape of digital healthcare. On the left side of our framework, we have the patient's local environment. This local node continuously generates dense, highly personal clinical data, such as real-time electrocardiograms, or ECGs. On the right side, we have the cloud hospital, a centralized infrastructure equipped with powerful deep learning models, such as convolutional neural networks, capable of detecting early signs of cardiovascular diseases far earlier than a human specialist. However, connecting these two nodes exposes a critical vulnerability regarding data in use. Standard cryptographic protocols, such as TLS or SSL, do an excellent job of protecting your medical records while they are in transit across the network. Furthermore, standard symmetric encryption like AES protects data at rest in the database. But there is a fatal gap. The moment the cloud AI needs to run its diagnostic inference, the data must be completely decrypted in the server's memory. This brings us to our specific threat model, the honest but curious adversary, also known as a semi-honest server. In this threat model, we assume the cloud provider will faithfully execute the diagnostic algorithms without tampering with the computation. However, they are curious, meaning the server administrators, data brokers, or an insider threat can monitor memory states, analyze access logs, and attempt to harvest your raw medical history. Unlike a compromised password that can easily be changed, your biometric and clinical data is immutable. Once your raw ECG is exposed in plaintext on a remote server, it is permanently vulnerable to unauthorized profiling and advanced persistent threats. This is the exact deadlock HERS is engineered to break. By activating the fully homomorphic encryption shield at the patient's local node, we completely eliminate the need for server-side decryption. The cloud will compute its complex neural network layers directly on the ciphertexts. We achieve true blind medical diagnosis, leveraging the computational supremacy of the cloud, while mathematically restricting the privacy perimeter exclusively to the patient's own device. Before any encryption can occur in the HERS pipeline, we must address a massive structural and computational bottleneck. Look at the patient's local environment. The raw medical data generated here, such as a continuous electrocardiogram or ECG signal, is not just a single, simple number. It is a high-frequency, continuous stream of analog data. To process this using any deep learning model, the local device must first digitize this continuous wave into a dense, high-dimensional array of floating-point values. Now, consider the naive approach to encrypting this array. Fully homomorphic encryption schemes naturally operate on massive polynomial rings, making a single ciphertext extremely large, often several megabytes in size. If we were to encrypt each individual heartbeat data point, like 0.85 or 1.20, into its own separate ciphertext, we would trigger a catastrophic explosion in both memory footprint and computational overhead. A simple vector of a few thousand floats would quickly balloon into gigabytes of encrypted data, making real-time network transmission and cloud computation practically impossible. To overcome this fatal limitation, HERS leverages one of the most powerful features of the CKKS homomorphic encryption scheme, SIMD, which stands for single instruction, multiple data batching. Instead of encrypting numbers one by one, the CKKS scheme allows us to mathematically pack thousands of discrete floating-point values into the independent message slots of a single plaintext polynomial. In our specific architecture, we utilize a polynomial degree that provides 4096 packing slots. This means a single plaintext object encapsulates an entire time series segment of the ECG. With our medical data efficiently packed into a single plaintext polynomial, the HERS pipeline advances to the critical cryptographic phase, fully homomorphic encryption. Notice the introduction of the patient's public key. In traditional systems, we might use standard RSA or elliptic curve cryptography. However, to enable homomorphic operations, HERS relies on lattice-based cryptography, specifically the ring learning with errors, or ring LWE, mathematical assumption. This not only allows for computation on encrypted data but also inherently provides robust post-quantum security against future quantum computing attacks. As the plaintext and the public key enter the encryption module, a highly complex transformation occurs. We are not simply scrambling bits. The encryption algorithm intentionally injects a meticulously calibrated, high-entropy mathematical noise into the polynomial. This noise addition is the absolute cornerstone of lattice-based security. It guarantees semantic security, specifically indistinguishability under chosen plaintext attack, or INDCPA. This ensures that even if the exact same ECG data is encrypted multiple times, it will produce a completely different ciphertext every single time, completely thwarting any statistical pattern analysis. The output of this module is our encrypted health data. It is crucial to understand that this is vastly different from a standard symmetric ciphertext. An AES ciphertext, for example, is a rigid, opaque block of bits. In contrast, our FHE ciphertext typically consists of a pair of massive, high-degree polynomials. It securely hides the patient's data while perfectly preserving its underlying homomorphic algebraic structure, allowing it to be mathematically manipulated. Finally, this massive ciphertext is transmitted across the public internet to the cloud hospital infrastructure. During this transit, the data is cryptographically bulletproof. Even if a highly sophisticated attacker intercepts this specific network packet, they are confronted with solving the shortest vector problem on a multidimensional lattice, a task considered mathematically infeasible. Once it arrives at the cloud, the server possesses a computationally malleable, yet completely opaque representation of the patient's clinical history. The stage is now set for blind AI inference. With the encrypted data now inside the cloud CNN, we collide with the most notorious bottleneck in FHE, nonlinear activation functions. Notice the ReLU graph on screen. Deep learning depends on these nonlinearities to learn abstract medical patterns. However, ReLU is a piecewise function requiring a greater than comparison. Here lies the fundamental incompatibility. FHE schemes, like CKKS, restrict us entirely to polynomial arithmetic. We are confined strictly to homomorphic addition and multiplication. Because encrypted data inherently blocks branching logic and comparison operations, evaluating a standard ReLU activation on a ciphertext is mathematically impossible. To bypass this roadblock, HERS employs a radical architectural shift, polynomial approximation. As you can see on the screen, we replace the sharp, non-computable ReLU boundary with a smooth, low-degree polynomial curve. In this simplified visual case, the square function, $y equals x caret $2. Why does this work? Because computing $x caret $2 requires only a single homomorphic multiplication, an operation perfectly supported by the CKKS scheme. By substituting all nonlinear activation layers with polynomial approximations, we trick the network. We provide the essential nonlinearity required for deep feature extraction, but we do so using exclusively valid homomorphic operations. Of course, this cryptographic workaround is not without its trade-offs. Replacing ReLU with a polynomial alters the mathematical landscape and convergence dynamics of the neural network. This requires us to carefully retrain the medical model from scratch to maintain high diagnostic accuracy. Furthermore, computing these polynomials consumes our most precious cryptographic resource, the multiplicative depth. Every time we approximate an activation function via multiplication, we inject more noise into the ciphertext, which leads us directly to the critical concept of the noise budget. To evaluate our polynomial approximations, the cloud CNN must perform sequential homomorphic multiplications. However, this introduces the most stringent cryptographic limitation in the CKKS scheme, the multiplicative depth constraint. Notice the noise budget meter appearing on screen. In lattice-based cryptography, security relies on the learning with errors assumption. This means every freshly encrypted ciphertext inherently contains a small amount of random mathematical noise. Without this initial noise, the encryption could be easily broken by linear algebra attacks. We refer to the maximum tolerable limit of this noise as our noise budget. As our encrypted tensor enters the CNN, watch the noise meter closely. In FHE, homomorphic addition only adds noise linearly, which is highly manageable. But homomorphic multiplication, which is strictly required for every single polynomial activation and feature convolution, causes the noise to multiply and grow exponentially. As the tensor passes through CONV1, CONV2, and CONV3, the meter shifts from green to yellow and plummets into the red zone. This visualizes the rapid degradation of our plaintext precision. If the accumulated noise breaches the upper threshold, meaning the budget drops to zero, the mathematical noise will completely overlap and drown out the encoded medical features. If that happens, the ciphertext is permanently corrupted, resulting in catastrophic decryption failure. This is exactly why deploying deep learning over FHE is incredibly challenging. While we could theoretically use a cryptographic technique called bootstrapping to clean the ciphertext and refresh the noise budget midway, bootstrapping operations are notoriously slow and computationally prohibitive for real-time medical systems. Therefore, the HERS architecture is fundamentally driven by this budget. The model is meticulously optimized to be intentionally shallow. We mathematically constrain the CNN to perform the exact minimum number of convolutions required to achieve an accurate clinical diagnosis, successfully extracting the final encrypted diagnosis just moments before the noise budget is completely exhausted. The diagnostic inference is now complete. Look at the output currently traversing the network back to the patient. The cloud hospital has successfully executed a deep convolutional neural network on the patient's ECG data, yet, remarkably, the server is entirely blind to what it just computed. The cloud does not know if the patient is suffering from arrhythmia, or if their heart is perfectly normal. It merely performed algebraic manipulations on encrypted polynomials and produced a new, highly compressed ciphertext. This encrypted diagnosis is now safely transmitted back across the public internet. Because the data remains in its homomorphic ciphertext state, it is immune to network sniffing, man-in-the-middle attacks, or any form of interception. The encrypted result now safely arrives back at the patient's local environment. This brings us to the absolute core of the HERS architecture, the Zero Trust Privacy Perimeter. Notice the introduction of the secret key. In asymmetric homomorphic encryption, while the public key is used to lock the data and perform cloud computations, only the corresponding secret key can reverse the mathematical noise and unlock the final result. Throughout this entire lifecycle, from the initial ECG reading to the final AI inference, this secret key has never once left the patient's device. It was never shared with the hospital, it was never uploaded to the cloud, and it was never transmitted over the network. We have established a mathematically enforced trustless system. The patient does not need to trust the cloud provider's security policies, because the mathematics of lattice cryptography guarantees their privacy. Now, with a single, highly efficient local operation, the patient's device applies the secret key to the decryption module. The cryptographic noise that accumulated during the cloud's neural network processing is finally stripped away. The underlying plaintext polynomial is revealed and evaluated against the diagnostic threshold, and there is our output, a definitive, plaintext clinical diagnosis, in this case, healthy. The loop is closed. The patient receives world-class, AI-driven medical insights instantly, entirely processed on edge and cloud infrastructure, without ever exposing a single raw data point. As we conclude this architectural deep dive, let us reflect on the broader implications of the HERS framework. Today, the rapid advancement of artificial intelligence in healthcare is constantly colliding with strict data protection regulations like GDPR and HIPAA. Medical institutions are paralyzed by the fear of data breaches, severely limiting the deployment of life-saving AI models. HERS represents a fundamental paradigm shift. It proves that privacy and utility are not mutually exclusive. We do not have to surrender our fundamental human right to privacy in order to benefit from the computational supremacy of the cloud. By bridging deep learning with fully homomorphic encryption, we are paving the way for a future where intelligent, predictive telemedicine is accessible to everyone, fundamentally secured not by trust, but by the irrefutable laws of mathematics. Welcome to the final, and perhaps most complex, architectural demonstration of our presentation, private image matching. In our previous sections, we secured one-to-one individual authentication and protected clinical health records. Now, we are scaling our cryptographic ambition to a much broader and more challenging problem: secure database retrieval. Let us first examine the fatal flaw in how traditional database systems operate today. Currently, to perform a search, the client must transmit their query image to the centralized server. We heavily rely on transport layer security, or TLS, to encrypt this data while it travels across the network. This protects the image from external hackers or man-in-the-middle attacks during transit. Furthermore, the database itself might be encrypted at rest. However, there is a fundamental cryptographic gap when the data arrives at its destination. The moment the server needs to execute the search algorithm, it must decrypt the query image into plaintext inside its system memory. This exposes the system to a critical vulnerability known as query leakage. Even if we completely trust the server to not be hacked by outsiders, we must consider the honest but curious threat model. An insider threat, a curious database administrator, or a compromised server log can instantly see the exact image the investigator is looking for. In high-stakes scenarios, the intent of the search is just as sensitive as the data itself. If a hospital queries a DNA sequence for a rare genetic disorder, or an intelligence agency searches for a specific political figure, exposing the query immediately compromises the entire investigation. The server learns who you are targeting, when you are targeting them, and what your motives are. This specific vulnerability, the exposure of the client's intent, is exactly what private image matching is engineered to eradicate. By deploying fully homomorphic encryption, we transition from standard database retrieval to zero-knowledge querying. In this advanced paradigm, the client mathematically locks their query image before it ever leaves their local device. The server will be forced to compute the complex visual matching algorithms directly on the ciphertext. It will scan its entire database and return the matching result, while remaining completely and mathematically blind to what the investigator is actually searching for. Let us see how this cryptographic process unfolds. To execute this zero-knowledge query efficiently, we must address a monumental computational bottleneck. A standard high-resolution image consists of millions of individual pixels. If we were to naively encrypt the raw image, applying the fully homomorphic encryption algorithm to every single pixel color channel, the resulting ciphertext would explode in size. It would generate gigabytes of encrypted data for just a single image. Transmitting this across a network, let alone computing deep learning convolutions on it at the server, is entirely impractical. Therefore, HERS and private image matching adopt an edge computing architecture. The pre-processing begins entirely locally at the client's secure environment. As you can see, the raw query image is passed through a lightweight, pre-trained convolutional neural network deployed directly on the investigator's device. This local CNN acts as a highly optimized feature extractor. Instead of outputting an image, it distills the complex facial structures into a dense, one-dimensional feature vector, often referred to as an embedding. Look at the vector now generated on screen. This array of floating point numbers, perhaps 256 or 512 dimensions, captures the absolute semantic identity of the subject. This step inherently adds a foundational layer of privacy, as a feature vector cannot be easily reverse-engineered back into a human face. However, to achieve true cryptographic guarantees against an untrusted national database, this plaintext vector is still not secure enough. It must be encrypted before it touches the internet. This brings us to a brilliant optimization in modern lattice-based cryptography. If we encrypted each of the 512 floating point numbers into 512 separate ciphertexts, we would still face a massive network overhead. To solve this, we utilize the SIMD, single instruction, multiple data, capability intrinsic to the CKKS homomorphic scheme. Notice the plaintext block with 4096 slots. In the CKKS scheme, a single plaintext object is represented by a high-degree polynomial. We can mathematically pack our entire 512-dimensional feature vector into the independent coefficients, or message slots, of this single polynomial. Watch as the vertical vector rotates and is smoothly compressed into the plaintext slots. This batching technique means that any homomorphic operation the server later applies to this ciphertext will be executed on all 512 features simultaneously, providing a massive degree of parallel computation. Finally, we reach the encryption phase. The client applies their specific public key to this densely packed plaintext polynomial. Through the ring learning with errors mathematical assumption, highly calibrated noise is injected, completely obfuscating the data. The result is a single, highly compact encrypted query vector. This ciphertext effectively locks the entire semantic identity of the subject into a mathematically robust vault. The client now transmits this single ciphertext across the network to the central database. Because of the local feature extraction and SIMD packing, the network payload is incredibly small, only a few megabytes. The server receives the package, completely blind to the numbers inside, perfectly setting the stage for homomorphic database retrieval. Now that the securely encrypted query vector has reached the central database, we face the core challenge of private image matching, the one-to-end search over encrypted space. The server holds millions of reference vectors, represented by the database grid. To identify a suspect or medical match, it must compute the similarity between the encrypted query and every plaintext vector. In standard machine learning, we might use cosine similarity or Manhattan distance. However, fully homomorphic encryption limits us to polynomial additions and multiplications. Calculating square roots or dividing by vector norms in the encrypted domain is computationally devastating. Therefore, HERS relies on the squared Euclidean distance, represented by the formula on the screen, $d2 =\sum, Q_I_V_I, $2. This metric is chosen not only for geometric accuracy, but also because it is perfectly compatible with the CKKS encryption scheme. We only need subtraction and multiplication to execute it. Let us break down this homomorphic evaluation step by step. First, the server must broadcast the encrypted query vector to align with the massive scale of the database. Notice how the query is duplicated across all reference columns. The first arithmetic operation is homomorphic subtraction. The server subtracts the plaintext database vectors from our encrypted query tensor. In lattice-based cryptography, adding or subtracting a plaintext from a ciphertext is a relatively cheap operation. It alters the underlying polynomial structure to represent the mathematical difference, but causes almost zero expansion to the ciphertext size and barely consumes our cryptographic noise budget. The result is a new set of ciphertexts, shown here as the difference blocks. At this moment, the server holds the precise numerical differences for every facial feature, yet because it remains wrapped in ring learning with errors encryption, the server cannot read a single value. However, a simple difference includes negative values, which cancel out when summed. To calculate true geometric distance, we must square these differences. This is where we hit the most critical computational bottleneck in our architecture, homomorphic squaring. Watch the noise meter on the right closely as the squaring operation executes. Multiplying two ciphertexts together, even multiplying a ciphertext by itself, is extremely resource-intensive. It causes underlying lattice dimensions to explode, requiring relinearization to bring the ciphertext back to a manageable size. More critically, this multiplication causes the inherent mathematical error, the noise injected during initial encryption at the client's device, to grow exponentially. You can see the noise budget immediately dropping and shifting to warning yellow. This is the multiplicative depth penalty discussed earlier. Every squared Euclidean computation brings the ciphertext one step closer to catastrophic data corruption. Despite the heavy consumption of the noise budget, the CKKS parameters were meticulously designed to withstand exactly this depth. The computation concludes successfully without breaching the noise threshold. The output of this entire parallelized operation is represented by the array of red blocks you see now, the encrypted distances. Think about the magnitude of what the server has just achieved. It has taken a high-dimensional encrypted vector, compared it geometrically against an entire database, and generated precise distance scores. Yet, from the server's perspective, it has merely manipulated high-entropy polynomials. It does not know which distance score is close to zero, and which is large. It cannot rank them, and it cannot filter them. The server possesses the exact answer to the investigator's query, but it is mathematically blinded from perceiving it. The cloud server has successfully completed the parallel geometric computations. However, it now faces the ultimate cryptographic roadblock. In traditional programming, finding the closest image match is a trivial task. You simply run a sorting algorithm or an argmin function to find the lowest distance score. But remember the fundamental limitation of fully homomorphic encryption: it does not support branching logic or comparison operations. To the server, an exact match with a distance of 0 looks mathematically identical to a complete mismatch with a distance of 100. The ciphertexts are indistinguishable. Because the server is mathematically incapable of determining which encrypted block holds the winning score, it has no choice but to transmit the entire array of encrypted distances back across the network to the investigator's client device. Look at the payload as it crosses the zero-trust boundary, leaving the untrusted cloud and re-entering the secure local environment. As the encrypted payload arrives, we invoke the final, definitive step of the HERS and private image matching architecture, local decryption. Notice the introduction of the secret key. Throughout this entire complex lifecycle, from the initial local feature extraction to the homomorphic squaring on the centralized cloud, this secret key has remained strictly confined to the investigator's physical device. It is the absolute anchor of our zero-trust model. The client device now applies this key to the encrypted array. The complex lattice noise, the error that was intentionally injected during encryption and compounded during the homomorphic multiplications, is now mathematically subtracted and discarded. The impenetrable ciphertexts dissolve, collapsing back into their original polynomial rings, and finally, into readable floating-point values. With the decryption complete, the true squared Euclidean distances are finally revealed in plaintext. We can see the array of scores, 5.22, 9.81, 0.04, and 6.15. Now, operating safely within the trusted local environment, the client device's CPU executes a standard, plaintext argmin function. Watch the visual representation as the algorithm iterates through the array. It evaluates the first score, moves to the second, and immediately identifies 0.04 as the absolute minimum. In geometric terms, a distance approaching 0 indicates that the query feature vector and the database feature vector are practically identical. The system confirms the minimum value, and the exact database record is successfully retrieved. The investigator has obtained their intelligence. The match is retrieved. But look at what we did not do. The server never saw the query face. It never knew who the investigator was looking for. It never knew which database record triggered the match. This brings us to the conclusion of our presentation. From the mathematical foundations of lattice cryptography in Act 1, to the integration of deep learning convolutions in Act 2, and finally to deployments like cryptoface and private image matching in Act 3, we have demonstrated a paradigm shift. For decades, the tech industry believed that data utility and data privacy were a zero-sum game. We believed that to use cloud AI, we had to sacrifice our privacy. Fully homomorphic encryption proves this is a false dichotomy. By combining advanced cryptography with machine learning, we can build a future where privacy is not just a policy, but a mathematical guarantee. Thank you for joining us on this journey. Welcome to our next practical demonstration, Medical FHE for X-ray Priority Triage. In the healthcare sector, hospitals are under immense pressure to quickly triage patient X-rays. While cloud-based AI diagnostics offer immense computational speed, there is a fundamental conflict. Strict data privacy regulations, such as HIPAA, strictly prohibit the transmission of unencrypted, personally identifiable medical images to untrusted third-party servers. To resolve this, we propose an architecture combining edge computing with fully homomorphic encryption. Observe the system layout currently on screen. On the left, we have the strictly regulated and trusted environment, the secure hospital client. On the right, we have the highly powerful, but mathematically blinded environment, the untrusted cloud server. The triage process begins entirely locally. A high-resolution chest X-ray is captured and loaded into the hospital's secure edge device. In a traditional workflow, this massive matrix of pixels would be sent directly to the cloud. However, homomorphically encrypting millions of individual pixels is computationally devastating and creates an unacceptable network bottleneck. Therefore, our architecture intercepts the data at the source. We introduce an edge feature extractor. Before any encryption takes place, the local hospital hardware runs a lightweight, standard plaintext algorithm to analyze the image. Watch as the raw X-ray is passed through this local extractor. Instead of outputting a full image, the algorithm distills the complex biological structures into a highly compact, 10-dimensional plaintext feature vector. This 1D array captures critical diagnostic indicators, such as global brightness, localized contrast, and structural edge energy. By reducing a massive image matrix down to just 10 essential floating point numbers, we drastically reduce the computational payload. This edge preprocessing step is the crucial optimization that makes the subsequent homomorphic encryption not just mathematically possible, but practically highly efficient for real-time medical triage. Now that we have successfully extracted the 10-dimensional plaintext feature vector, we must secure it before it ever leaves the hospital's local network. To achieve this, we introduce THONG, a highly specialized cryptographic library engineered specifically to perform homomorphic operations on tensors. As you can see on the screen, the system initializes an encryption context using the CKKS scheme. Why do we choose CKKS? Because it natively supports homomorphic arithmetic on floating point numbers, which is an absolute requirement for evaluating machine learning models. We set the poly_modulus_degree to 8192. This parameter provides a perfect architectural balance. It guarantees a robust level of security against modern cyber threats, while allocating just enough noise budget to support our linear classification. With the cryptographic environment established, the edge device invokes the hospital's public key. Watch closely as the encryption process is executed. The public key mathematically locks the 1D feature array. The continuous floating point values of the patient's biological data are encoded into high-degree polynomials. Simultaneously, a carefully calibrated layer of cryptographic noise, based on the ring learning with errors assumption, is injected directly into the data. The output is a highly secure, encrypted tensor known as a CKKS vector. The patient's sensitive medical data is now completely obfuscated, locked behind an impenetrable mathematical vault. Because this is an asymmetric protocol, the public key can only lock the data. The corresponding secret key, the only mathematical tool capable of reversing this noise, remains strictly confined to the hospital's local server. With the payload cryptographically secured, the hospital can now safely transmit this locked CKKS vector across the public internet to the untrusted cloud server. This transition solves the fundamental roadblock of healthcare data regulations like HIPAA. Even if the network traffic is intercepted by a man-in-the-middle attack, or if the cloud infrastructure is completely compromised by a malicious hacker, the attacker will obtain nothing but random, unintelligible polynomial noise. The data is now secure in transit, secure at rest, and perfectly staged for blind computation. The encrypted X-ray features have safely arrived at the untrusted cloud server. The server holds a pre-trained linear triage model, represented here by the plaintext model weights and the bias value. In a standard machine learning pipeline, generating a diagnostic prediction involves calculating the dot product of the input features and the weights, followed by adding the bias. Remarkably, the THONG library allows the server to execute this exact algebraic formula directly on the ciphertext. Because the server is performing operations between an encrypted tensor and plaintext model weights, we refer to this as a ciphertext plaintext evaluation. Watch as the homomorphic evaluation unfolds. The server mathematically multiplies its plaintext weights with the encrypted feature vector and adds the plaintext bias. These inputs seamlessly merge to form a single, newly computed tensor, the encrypted logit. Now, pay close attention to the cryptographic noise bar on the right. In our previous demonstrations with deep neural networks, we saw how continuous homomorphic multiplications rapidly depleted the noise budget, risking catastrophic data collapse. However, because this is a linear triage model, the entire evaluation requires a multiplicative depth of exactly 1. Notice that the noise level barely drops. This architectural decision, extracting complex features on the local edge and strictly limiting the cloud to shallow linear homomorphic operations, is the definitive key to achieving real-time, privacy-preserving medical diagnostics without exhausting the server's computational resources. The cloud server has successfully computed the encrypted logit. However, a raw logit is simply a linear continuous value, it is not a clinical probability. To make a diagnostic decision, we must apply a nonlinear activation function, such as sigmoid. Here lies a critical optimization in our architecture. In fully homomorphic encryption, calculating a precise nonlinear sigmoid curve requires highly complex Taylor polynomial approximations. Forcing the cloud to compute this would consume a massive amount of the multiplicative depth, destroying our computational efficiency. Therefore, the cloud strategically stops here and returns the encrypted logit back to the secure hospital client. Upon receiving the locked ciphertext, the hospital's edge device applies its secret key. The cryptographic noise is instantly stripped away, revealing the precise plaintext logit value of 2.45. Now, operating safely within the trusted local environment, the edge device can perform the nonlinear sigmoid activation in plaintext, requiring zero cryptographic overhead. Let us visualize this mathematical transformation. On the screen, we plot the sigmoid activation curve. The horizontal axis represents the raw logit values, while the vertical axis mathematically compresses these values into a strict probability range between 0 and 1. Watch as our specific patient data point is mapped onto this function. The patient's logit of 2.45 is plotted on the horizontal axis. We project this vertically onto the sigmoid curve, and then horizontally to the probability axis. The mathematical transformation perfectly calculates a diagnostic probability of 0.91, meaning there is a 91% confidence level regarding the triage condition. With the probability established, the system makes a deterministic clinical decision. For this specific medical model, the diagnostic threshold is set at 0.5, represented by the red dashed baseline. Any probability above this line demands immediate medical attention. As you can clearly see, our patient's probability sits well inside the critical zone. The local system instantly triggers the response logic, flagging the patient as urgent. The untrusted cloud successfully triaged the patient without ever seeing the X-ray, the extracted features, or the final result. Absolute medical privacy has been mathematically guaranteed.